Hello, my name is Ron Smith. Worlds Without Number introduces countable and uncountable numbers from a mathematical point of view. This is the fourth video in a series I call A Latter-day Saint Mathematician Looks at God. Consider these lines from a revelation given by Joseph Smith. Worlds without number have I created, and numberless are they unto man, but they are numbered unto me, for they are mine, and I know them. The heavens, they are many, and they cannot be numbered unto man, but they are numbered unto me, for they are mine. A good friend of mine recently asked me, is there a number so large that it cannot be counted? The surprising answer is yes. In fact, there are many numbers that mathematicians call uncountable. By the end of this video, you will have seen an uncountable set, and hopefully you'll understand why it's uncountable. Let's start with the numbers that you learn to count with. 1, 2, 3, 4, 5. They're called natural numbers by mathematicians. This is a very large set of numbers, as you know, and it has a property that seems very strange when you first see it. Imagine a list of all of the natural numbers. Here they are in the blue box. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It, of course, goes on forever because this is an infinite set. Now, I want you to imagine multiplying each number by 2. There you go. You didn't change where anything was, but you multiplied by 2. Has the number of numbers in the list changed? If not, the number of numbers must be the same as the number of natural numbers. Hold it! Flag on the play! How can the number of even numbers be the same as the number of natural numbers when half of the natural numbers are missing? I told you this would seem strange. To resolve this paradox, we need to understand what I will call the school bus principle. Suppose all the children get off of a school bus in pairs. Each boy is holding one girl's hand, and vice versa. What can you say about the number of boys and girls originally in the bus? Clearly, the number of girls and the number of boys must be equal. We can tell if two sets have the same number of members, even if we haven't counted either set. If the members of two sets can be paired so that none are left over, then the number of members must be the same. Let's apply this to the even numbers. The even numbers can all be paired with the natural numbers with none left over. Mathematicians call such a pairing a one-to-one correspondence. And when there's a one-to-one correspondence between a set and a part of itself, then the set is infinite. And this is the definition that we use for infinity. Now, you may have learned that infinity means something like it goes on forever, or never-ending, or bigger than anything. But this is a better definition because this turns out to be applicable to all the infinite sets that we'll see, and we'll see that there are different sizes of infinite sets. So even though it seems strange when you first see it, this turns out to be a very useful idea. Let's look at the number of fractions. You know what fractions are. We can list all of the fractions that have denominator 1. 1 over 1, 2 over 1, 3 over 1, 4 over 1, 5 over 1, etc. We can list all of the fractions with denominator 2. 1 half, 2 halves, 3 halves, 4 halves, 5 halves, etc. We can list all the fractions with denominator 3 and all the fractions with denominator 4, etc. Now, there are a lot of fractions. We have infinitely many on the first row. We have infinitely many rows. So the question is this a bigger infinite set than the natural numbers, or is it the same size? To find out, we need to know if there's a one-to-one correspondence between this set and the natural numbers. In other words, can we list these in order with the first one, the second one, and so on? So we're going to take a look at diagonals and instead of rows. And you'll notice that in the first diagonal, there is one number, fraction. In the second diagonal, there are 2 fractions. In the third diagonal, there are 3 fractions. In the fourth diagonal, there are 4 fractions. In the fifth one, 5 fractions, and so on. And what we have at the bottom of the screen is a list of all of the fractions in order. There's a first one, a second one, a third one, a fourth one, a fifth one, sixth one, etc. The fractions can be listed in order with none left over. So by the school bus principle, the number of fractions is the same as the number of natural numbers. How's that for strange? We call such sets countable. Now let's look at 0-1 sequences. A 0-1 sequence is a sequence with just zeros and ones. There are lots of them, and here's a bunch that I just made up out of the top of my head. If you like, why don't you make up some and write them down? You can make any ones you want as long as they just have zeros and ones, and as long as each sequence goes on forever, then your list will be as good as mine. Now let's suppose that we can list all of the 0-1 sequences. If we could, then we could put a number by each one. We'd have a first one, a second one, a third one, fourth one, fifth one, sixth one, like you see here, etc. Now we're going to do something that mathematicians do a lot. We suppose that something is true, and then we look for a logical contradiction. And once we come up with a contradiction, then we'll know that what we supposed couldn't be true. So we're supposing that we can list all of the 0-1 sequences. And we're going to construct a sequence that isn't in the list. So let's look at the diagonal. My list has a diagonal, your list has a diagonal, no matter what it was. And the diagonal is a sequence of zeros and ones. Let's complement the diagonal. Some people might say, oh, what nice zeros you have. But that's not the kind of complement that we mean. We mean take the opposite one. If there was a 0 in our diagonal, we're going to put a 1 down. If there's a 1 in our diagonal, we'll put a 0 down. And so the red sequence of zeros and ones is the complement of the blue one. Now notice that the complement is not the first sequence in the list because the first digits are different. The complement is not the second sequence in the list because the second digits are different. It can't be the third one in the sequence because the third digits are different. It can't be the fourth one or the fifth one or the sixth one. In fact, it can't be anywhere in the list. And since no list can contain the complement of its diagonal, the number of 0-1 sequences is uncountable. It can't be listed. Wow, isn't that strange? But that's a really made-up set of numbers or set of things. Are there any real things that have uncountably many? Well, let's take all of these 0-1 sequences and let's put a 0 and a decimal point in front of each one. Then each 0-1 sequence represents a real number between 0 and 1. This shows that the number of real numbers between 0 and 1 is uncountable. In fact, the number of numbers between any two real numbers is uncountable. So do these infinite numbers have names? Well, Georg Cantor, who was born in 1845, is called the father of set theory. He was the first mathematician to write about uncountable sets. He chose the name Aleph Naught for the number of natural numbers. The letter Aleph is the first letter of the Hebrew alphabet, and the subscript 0 is called naught, N-A-U-G-H-T, an old word for zero or nothing. Some people call it Aleph null. Georg Cantor believed that understanding infinity would help us to understand God. he wrote, "From me, Christian philosophy will be offered for the first time the true theory of the infinite." Now, if you're not totally blown away by the notion of more than one infinite number, then you're probably asking this question: what is the number of 0-1 sequences called? We can list all of the 0-1 sequence with 3 digits, and if we do, there's the list. And how many are there? Well, there are 2 ways to fill in the first slot, 0 or 1. There are 2 ways to fill in the second slot and 2 ways to fill in the third slot, giving us 2 times 2 times 2, or 2 cubed ways to have 0-1 sequences with 3 digits. So the number of 0-1 sequences with alpha naught digits is 2 times 2 times 2, da 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 da, which is equal to 2 to the aleph naught. And that makes a very nice name for this number. We've shown that aleph naught is actually less than 2 to the aleph naught. The countable infinity is less than uncountable infinity. Well, now that you've seen 2 of them, you might be asking, are there larger infinities? And I'm just going to answer this quickly for those of you who might have asked this question. If this is not your question, then hang on for just a little bit and we'll get to the faith lesson really fast. The proof that we've given that aleph naught is less than 2 to the aleph naught is easily adapted to show that aleph naught is less than 2 to the aleph naught is less than 2 to the aleph naught is less than ... So there are at least aleph naught infinite numbers. How's that for a mind boggler? Are there even more than aleph naught infinite numbers, you might ask yourself? This question turns out to be undecidable with the usual axioms of mathematics. In other words, there are consistent mathematical systems in which everything you and I know about mathematics is true, and there are no other infinite numbers. And there are consistent systems in which there are other infinite numbers. Okay, let's look at the face lesson. Infinite sets are so large that they can be put into a one-to-one correspondence with a proper subset of themselves. This gives an interesting analogy for the relationship between the Father and the Son being one and yet not the same. Perhaps it's a one-to-one correspondence with a proper subset. Second, both countable and uncountable numbers exist. This gives an interesting interpretation to the words that we started with. Worlds without number have I created, and numberless are they unto man, but they are numbered unto me, for they are mine, and I know them. Remember that God is bigger than we are. The heavens, they are many, and they cannot be numbered unto man, but they are numbered unto me, for they are mine. These words were published in 1830. A half-century later, Georg Cantor discovered uncountable numbers. Another half-century passed before Hubble discovered stars and galaxies other than the Milky Way. Have a blessed day.